Hi everyone, welcome to GateWay lectures. Here we have a good question in fluid mechanics regarding the plate and multifluids. Let's go through the question. Fluid of viscosity mu1 is equal to 0.1 Newton second per meter. Yes, that is unit of the viscosity. Mu2 is equal to 0.15 Newton second per meter are contained between, these are the absolute viscosities, are contained between two plates. So there is a plate above which is movable plate and plate below is a fixed plate. And the area of the plate is given as 1 meter square. The thickness are H1 is equal to 0.5 mm and H2 is equal to 0.3 mm. Find the force F to make the upper plate move at a speed of 1 meter per second. What is the fluid velocity at interface between the two fluids? Assume linear velocity profiles. See here it is given mu1 as a medium. So this is one different fluid having a viscosity 0.1 and this is a different fluid having a viscosity of 0.2, and here it is said to assume a linear velocity profiles. Since mu1 is not equal to mu2, the slope will not be equal in both the cases. Though they are linear velocity profiles, the slope is not equal. Okay, and h1 h2 values are given. So, and also here one important thing to note is assume linear velocity profiles, and we'll make few concept basics clear here so that we can proceed to the question. If concept is not clear, we'll not get a way to solve the question. Let's go through the concept here. So here a concept is whenever there is given a linear velocity profile, so and between a fixed and movable plate, or between a fixed medium and a movable fluid, whatever may be, so always you remember that the velocity gradient du by dy always changes. We know as per Newton's law of viscosity, tau is equal to mu into du by dy. Okay, this velocity gradient is linear. So for linear velocity gradient, we know how to write the slope. Slope is nothing but du. Here the velocity is 0. Here the velocity equal to v. So du is nothing but change in velocity from v minus 0 upon dy. Here the height is h and here the y value is 0. So nothing but h minus 0. So this we get to be mu into v upon h. And also one more thing, important thing to notice here is as we move from bottom to top, as we increase the value of delta, as we increase the value of y, sometimes it is called as delta, the tau value doesn't change here. See, if velocity as we move to the top, v increases, also h increases, and they both increase in a linear fashion. So the slope remains the constant. So as we move towards the top at any point, let's say some point A and here somewhere point B and here somewhere point C, even though velocity of A is not equal to velocity of B is not equal to velocity of C, but tau of A is equal to tau of B is equal to tau of C. The shear stress is always the same at each and every point in the fluid for the linear velocity profile. This is the important thing for us to here to solve this question. This is only the basic required here to solve a question. So let's go through the question here. Linear velocity profile, we know tau is equal to constant. Just now we've learned the basic. So let us consider the interference layer initially. So first we'll calculate the velocity of interference layer, then we'll calculate the force required. See here we have taken the interference layer. This is the interference layer, and also if you can observe on the interference layer, it is having some velocity vi. So interference layer having velocity vi, and also here the fluid 2, whatever fluid 2 is present here, this fluid 2 whatever present here will try to pull the bottom fluid. Since the top plate is moving, that top plate tries to pull the fluid layer below it. So it applies a same shear force on the second fluid, on the fluid 2. So that fluid 2 also try to move along in the direction of the moving plate, but this bottom plate is fixed. The mu1 fluid, the first fluid, is in contact with the bottom plate, so it always try to keep in rest. So whenever it is trying to keep in rest and the top fluid is trying to move it, the interference will have a force, and that force direction will be in this direction. How will you get this direction? And this is nothing but Fs2. This direction you will get as this Fs2, we can call it as force applied by the first fluid on the second fluid. Nothing but we'll be representing it on the second fluid, right? Similarly, the force applied by the second fluid, this is the second fluid, this is the second fluid and this is the first fluid. Fs1 is nothing but force applied by the second fluid on the first fluid. So this second fluid always tried to move in the right direction, so it always tried to pull the layer in the first fluid at the interface towards the right. So the force here, it will be in the right side direction and its magnitude will be equal to Fs1. So this is the first fluid having mu1 viscosity, this is the second fluid having mu2 viscosity. So here if you can observe, at interface, for having some linear velocity, the forces should be balanced, the forces should be in equilibrium. If forces are not in equilibrium, there will be a torque created, right? We know that if the forces are not equal, there will be a torque created. Here Fs1 is equal to Fs2. And one more thing, suppose this interference is having some area AI, suppose interference is having some area AI, we know tau is equal to Fs into area. Okay, from that Fs is equal to, tau is equal to Fs upon area. Fs upon area. From that Fs is equal to tau into area, right? So here Fs1 we can write as at the interference. Since here area is nothing but interference area, we are taking at the interference. So Fs1 is equal to tau from the first fluid into, we know tau is same everywhere. Since for linear velocity profile we got the tau is same everywhere, even though we'll take tau 1 and tau 2 and to relate the condition to get the Vi values. So tau 1 into AI is equal to tau 2 into AI. So AI will be getting cancelled because interface on the both the fluids is having same area, and tau 1 we can write as mu into du upon that. So we can write as mu1 into du is nothing but, if you can observe the first fluid, its velocity at the bottom is 0, but the velocity at the interference is Vi. And for the second fluid, velocity at the bottom is Vi and the velocity at the top is V, that is equal to 1 meter per second, right? So if you consider first fluid, it is nothing but V interference minus 0 upon H1. H1 is 0.5, that we will substitute 0.5 mm. And tau 2 is equal to mu2 into IST is 1 minus, and interference value is Vi upon H2. The fluid film thickness is H2. By substituting, we know mu1 value, we know mu2 value, we know H1, we know H2. By substituting these values, we will get the value of Vi as 0.714 meter per second. Okay, we got the value of Vi. Now you calculate any shear stress, because we know in linear velocity profile the shear stress is constant all over. So you calculate any value, either tau 1 or A2. Here I am taking tau 1. So mu1 into Vi upon H1. Mu1 is known, Vi is known, H1 is known. From this we will get the value of tau I as 142.8 Newton per meter square. So here we need to calculate the force. See, this same tau 1, it is constant everywhere. So the same tau 1 will be acting at the interference of the plate also. So here the top plate, which is moving with some velocity, which is being applied with some force, which is moving with some velocity 1 meter per second. Whatever the shear stress applied at this interference, the same shear stress will be applied at the moving plate. So it will be in the opposite direction, right? Because stress is always a reaction force, so it will be in opposite direction. From that we can calculate force as, we know tau is equal to F by A. From that F is equal to tau into A. So tau 1 into area of this plate, and area of this plate is given as 1 meter square. So tau 1 is 142.8 Newton per meter square into 1 meter square. So the value of the force we will get as 142.8 Newtons. Thanks for watching. In this question, the only important thing to know is for linear velocity profile, tau is equal to constant. Tau doesn't vary with the distance, but velocity varies linearly. And coming back to like parabolic or cubic variation, the tau is not constant. Tau also varies. Okay, we'll be solving those questions also. Thanks for watching.